Hello everyone, and welcome back to another chapter of Physics 1030. Today we're going to start chapter 5, which is work, energy, and power. Now, all of these things are very closely related, and they all are words that you've probably seen outside of physics class. However, we're going to deal with more specific definitions for each of these words, narrow definitions that are used in the context of physics. So while you may think you know what work is, we have a very specific definition of what work is. So you might say what I'm doing right now is work. It's, something I'm getting paid for, part of a job. But that's not really work in physics. Though we'll see there are some analogies that you can make, particularly between, work and energy, that sort of relate back to being able to do the traditional type of work. But let's define these in terms of physics. So first off, work is defined as the process of energy transfer to an object via the application of a force. Work is giving or taking away energy from something. And those amounts of energy, they are given or taken away by forces. So we saw in chapter 3 that forces caused accelerations. When you applied a force to something, if there was a net force, it would accelerate and change its velocity. Something is very similar. In fact, these are very closely related. Changing something's velocity, we'll see, changes its energy. So applying a force can add or subtract energy to something, and that process, we refer to it as work, giving or taking away energy. So how do we define energy? Well, it may seem like circular logic, but energy is defined as the ability to do work. You can't do work if you don't have energy. And just as in physics, this is sort of true in real life. I had to wake up this morning and eat a good breakfast, drink my V8 energy juice, and that combination of calories and caffeine gives me energy, and now I can do work. So that's sort of an analogy, but it is the way it works in physics as well. If you don't have energy, you can't do work. You need to have energy to spend to be able to do work on something. And we're going to see several forms of energy. You can store energy in lots of different ways, and while you've got it stored, you then have the ability to apply it to something. You can then spend your energy budget on various things, doing work on various things, and we'll look at different examples as the chapter goes on. Lastly, I want to define power. Now, power sort of relates energy and work to time. Power is the time rate at which you can do work, or the time rate at which you consume energy. Power is defined by how much work you can do over a certain amount of time. And we'll start by focusing on work and energy, and we'll come back to power a little bit later in the chapter. So let's focus on the types of energy we'll consider. We're going to broadly split energy into two categories, at least as far as chapter 5 is concerned. And those two categories are potential energy and kinetic energy. Now, potential energy is just like the name suggests. It's energy that has potential. It isn't anything just yet, but we could take that energy and turn it into something. It's not grown-up energy. It's little. It's a little kid that has potential, and we want to know what it's going to be when it grows up. And we'll look at a couple of types of potential energy. There are many ways in which you can store energy, and we'll look at two of them in this chapter. We're only going to look at one form of kinetic energy, and specifically it would be referred to as translational kinetic energy. But that's a word I'm not going to use the rest of this chapter because we're only looking at that form. So we'll just broadly refer to it as kinetic energy. But that is the energy of motion, The word kinetic implies movement. Kinetic energy is the energy of motion. So if something is moving, if it has a velocity, it has kinetic energy. And a common exchange we'll look at is taking potential energy and turning it into kinetic energy. If I hold my pen above the table, it has potential energy. When I drop it, that potential energy turns into kinetic energy, the energy of motion. Now, I said this is translational kinetic energy, so it's about moving in a line. But there are other forms of kinetic energy. The next easy one to discuss is rotational kinetic energy. When objects spin, they have kinetic energy. But as I mentioned, we're not going to talk about that in this class at least. But I would like you to know there are other variations out there. But as far as Physics 1030 is concerned, we're just going to look at two types of potential energy and one type of kinetic energy. Now, I want to go ahead and dive right into equations to define these things. We're going to look at the definitions of work and energy now in terms of equations. We've seen them in words. Now let's look at them in an equation form. And so let's start with work. Work was defined, by adding or subtracting energy through the application of a force. So of course, force shows up in the equation. Work is defined by the capital letter W, and you can compute the amount of work done as force, F, times distance, D. But there needs to be a special relationship between the force and the distance. It needs to be the distance parallel to the force, or vice versa, the force parallel to the distance. They're parallel to each other, so really either way you phrase it is true. And really, that comes from this multiplication. That's in reality, in the bigger realm of physics, force is a vector. And really this is displacement, which we know to be a vector. And that multiplication is what is called a dot product. And the dot product automatically takes the parallel pieces. But that's something that's not really in our toolbox just yet. If you are familiar with dot products and the other vector multiplicative process, the cross product, great, but if you're not, don't worry about any of those things I just said. What you need to care about is finding the force that is parallel to the displacement or distance. And because we can't really give it the full vector treatment, we're not going to worry about using these in their vector forms. Don't worry about a positive or negative force or a positive or negative displacement. Just take the positive values and multiply them together, but make sure you take the parallel pieces. Well, if we're not dealing with direction, that tells us that energy is a scalar. And even if these two values were vectors, the dot product gives you a scalar in return. So energy is always a scalar. It's just a magnitude. Energy doesn't have direction. It just has an amount. But that is what work looks like. That is how we'll compute work directly. The next equation I want to look at is kinetic energy. Kinetic energy is typically given by capital K, capital E, KE, and it's defined by 1/2 mv squared. So your kinetic energy depends on your mass and your speed. Well, I just said velocity, but we then square it. And if you just think about our one-dimensional velocity, it's either positive or negative. Well, if you square a positive number, it's positive. If you square a negative number, it's positive. You lose the directional information when you square a quantity. So because this is velocity squared, it's really just speed. Only the magnitude or amount is what matters. And you can see because it is squared, it's going to have a larger effect on the total amount of energy. So yes, if you have more mass, that gives you more kinetic energy. But if you were to increase your velocity, you get a much bigger change in kinetic energy than if you were simply to increase your mass. The square has a more powerful effect than just the direct linear relation of mass and kinetic energy. So that is how kinetic energy is defined. Remember, we said it's the energy of motion. Obviously, if you have zero velocity, you have zero kinetic energy. And if you have any velocity, positive or negative, you end up with a positive kinetic energy. We're going to deal with positive energies in this class. There are ways to write physics problems and work with negative energies, but this is an introductory physics class. I'm going to try to keep the problems as simple and straightforward as possible, so we will work them in such a way that energy is always positive. We might take away some energies, you might still do some subtraction, but we'll be working with positive amounts of energy. Even if we're subtracting them, we'll be subtracting a positive amount. But in the big, broad world of physics, you can do fancier, trickier things where energy isn't always considered positive. All right, our next equation is gravitational potential energy. Now, this is one of the forms of potential energy that we'll look at. Potential energy is given by capital P, capital E. And since we're going to have different types of potential energy, we'll differentiate them with a subscript. So I've put a subscript G here for gravity. Now, when working problems, you might not always have to place that there. Again, we're trying to keep things simple in here. So I won't be mixing gravitational potential energy and elastic potential energy very often. I think I might give you a homework problem about it, but I won't be expecting you to differentiate between the two in, say, a testing situation. One might come up, but not both at the same time. That way you can't possibly get confused between, two different potential energy terms in the same question. All right, but anyway, back to the equation. Potential energy, gravitational potential energy, is defined by mgh. That m is your mass, so of course the more mass you have, the more potential energy you could have. G is indeed the acceleration of gravity, 9.8 meters per second squared. But remember, we're not worried about direction with energy. Energy is a scalar, so that is positive 9.8 meters per second squared. We'll be dealing with positive amounts of energy. So make sure to make that positive 9.8, not negative 9.8 meters per second squared. And lastly, we have the h. That h stands for height. And so the further up you go, the higher something is above the ground. We'll just refer to the ground as 0. We'll define that in our problems as we begin to work. You got to define where the origin is to be able to measure from it. But your height above 0 will also, impact how much gravitational potential energy you have. The farther up you are, the more energy you have stored, which could turn into something. If you drop something, it begins to move. It becomes kinetic energy. And the higher you drop something from, the more potential it has to turn into even more kinetic. It's going to move faster and faster by the time it hits the ground, the higher you drop it from. All right, let's look at our last form of energy that we're going to consider in this chapter. And that is elastic potential energy. And that is sort of the energy stored in a spring or a rubber band or anything that sort of stretches or compresses. Again, it is potential energy, so we call it PE. And since it's elastic potential energy, I've given it a subscript of E. It is PE sub E. And it is defined as 1/2 kx squared. Now that k is something new. That k is called a spring constant. And a spring constant defines how rigid a spring is, or how hard it is to stretch or compress. If we look at the units for k, they are newtons per meter. Newtons, that's how much force, and meters per meter tells you how much it's stretched, the amount it is stretched or compressed. So if this is a big number, it takes a lot of force to compress it some amount. If it's a little number, it doesn't take as much force. So if you think about like those big springs in your car, your shocks, that's going to have a very large spring constant. Those are very hard to compress. But if we had, the little spring in my pen, I can just with, one finger click it up and down. that would have a low spring constant. It doesn't take much force to stretch or compress it. So if we think about that spring constant, the bigger it is, the more potential energy we can store. If it's small, we cannot store as much potential energy. And the last term on this equation is x squared, where that x is the distance stretched or compressed. And that is the distance from equilibrium. So if your spring normally just sits here, you then measure how much it changes from its equilibrium state, how much it is stretched or compressed. And it works in either direction. You store energy by pulling a spring apart or by squishing it together. Either way works, and again, we square it, so we don't really see if it was negative for compression or positive for being stretched out. Either result gives us a positive amount of stored potential energy. Again, we're going to work these problems in such a way that we deal with positive amounts of energy. All right, well, this has been a brief introduction to work, energy, and power. We've defined those things, and we've now got a few equations to work with. But before we actually put them to use, before we apply them, I want to take a look at their units and see if we can get a deeper understanding of all of these forms of energy before we dive into any problems. So we'll pick up with the units of energy in our next video. See you then.